All right, I want to mention buffer capacity. The author actually mentioned buffer capacity in the very first section of the module, but I almost think it's maybe a little easier to understand that concept once you started working some problems, because you're able to understand the difference between the pH and exactly what's required to get that pH to change. Buffer capacity is defined as the amount of acid or base that can be added to a buffer solution before the pH changes significantly. Now, we've already seen no matter how much acid or base you add, the pH is going to change, but the change is small, at least for a while, until you run out of that acid or that conjugate base. And then at that point, then your pH is just going to shoot all over the place, okay? So to understand the concept of buffer capacity, let's compare two different buffer solutions. Let's compare a liter of a buffer that's made with 1 molar acetic acid and 1 molar sodium acetate. And let's compare that to a liter of a buffer made with a 1/10 molar acetic acid and a 1/10 molar sodium acetate. First of all, we have 1 liter of each, so the volume doesn't matter because it's the same for both of them. If you compare the Kas and the dissociations and the acid ionization constants and all of that, that isn't going to be affected either because I use the same ones for both. The only thing that's different is the concentrations of them. So if I compare the pH of these two, what's the pH difference going to be? Which one is going to have the higher pH? Well, again, if you remember, pH equals pKa plus the log of the concentration of the base over the concentration of the acid, right? Okay, well, it's the same weak acid, so this is the same in both of them. So what's different is going to be this ratio when I'm calculating pH. Although in this case, will this ratio be different? Because the base divided by the acid here, 1 divided by 1 is going to be 1. If I put the concentrations down here into this equation, I'm going to have 0.1 over 0.1, which is also 1. So the pH of both of those solutions is going to be the same. Okay? So the pH is the same, but the buffering capacity is not the same. Because if I calculate the number of moles of acid and the number of moles of conjugate base, which one has more? Right, this one does because the concentration is higher. So both of these two solutions will have the same pH for both of them, but this one is going to have the higher buffer capacity, because it just absolutely has more moles of stuff to react with whatever you're putting into it. Okay, so same pH for both of them, but this has a higher buffer capacity because it has more moles of acid and conjugate base in order to react. Okay, so buffer capacity. Now, back in Module 6, when we were discussing solubility equilibria, we also discussed the common ion effect. And so that common ion effect is going to come into play again in today's lesson because of when we are trying to dissolve hydroxides, we often have to take into account the fact that water also has hydrogen and hydroxide ions in it just by nature of the way water is. And because hydroxides don't generally dissolve well, sometimes they dissolve so little that we have to take into account the self-ionization of water to figure out how much of these guys are going to actually dissolve. So if I look at example 8.4, if I have aluminum hydroxide, and I know what the KSP of that is, it wants to know what the aluminum ion concentration would be in a saturated solution of aluminum hydroxide, okay? So to do this problem correctly, I have to realize that the KSP for aluminum hydroxide is very, very, very little. Aluminum hydroxide, again, if you don't recall how to do this, you may need to flip back to Module 6, but aluminum hydroxide as a solid doesn't dissolve readily, and so it set up an equilibrium with aluminum ions and hydroxide ions. And so when I write the KSP expression for this, I have the aluminum ion concentration times the hydroxide ion concentration cubed because of that 3 in front as a coefficient there. So if the KSP for this it's actually very small, it's 1.9 times 10 to the minus 33. Now, I could take the 4th root of that, but what you're going to see is that the hydroxide ion from the water that's there actually contributes quite a bit of hydroxide ion to this particular solution, and it's going to affect how much of the aluminum is actually going to be able to dissolve. So initially, I don't have any of the aluminum ion there, but if you'll recall, water, which has a pH of 7, will also have a pOH of 7. And so what that tells me is that in pure water, my OH concentration is going to be 1 times 10 to the minus 7th. Okay, that's going to be substantial when you compare it to the amount that we would otherwise calculate here. So the aluminum ion concentration is going to be just whatever dissolves. Okay, the hydroxide ion concentration, what I start out with is 1 times 10 to the minus 7th plus whatever is going to dissolve. And then this whole thing has to be cubed. Okay, now I am going to assume that this x is very little because otherwise I have a very nasty equation that I am really not going to be able to solve. So I'm going to assume that that's going to be little. And then when I divide that out, that's actually going to give me 1.9 times 10 to the minus 12th, okay? And so that actually then is also going to be the aluminum ion concentration here, all right? So what happens if I'm not dissolving something in pure water? What happens if I already have a higher pH when I start? Well, that's what example 8.5 is all about. So how many moles of chromium hydroxide can be dissolved in a liter of solution with a pH of 8? And they give us a KSP of 6.7 times 10 to the minus 31. I'm going to go ahead and write that down. Okay, so once again, very, very tiny number here. If I have a pH of 8, that's going to be a pOH of 6. And so therefore, my hydroxide ion concentration is going to be 1 times 10 to the minus 6. And so that's what the hydroxide ion is going to start out at initially, even before anything would start dissolving. So just like before, my chromium ion concentration is going to be X. My hydroxide ion concentration is going to be 1 times 10 to the minus 6th plus X. And that whole thing has to be squared. Once again, I have a very, very nasty equation that I have to solve if I can't assume that this is little. Luckily, we can assume that this is going to be small. And so when I solve this, my X comes out to be 6.7 times 10 to the minus 19th. Okay? And so for 1 liter, then this is also going to be my chromium ion concentration. Okay, so there, hopefully you can see that whenever you're trying to dissolve a hydroxide into water, since it already has such a very, very small amount that's going to dissolve anyway, the higher the pH is, because of that common ion effect, the less of that hydroxide you're going to be able to dissolve. So if you want to try to dissolve a hydroxide in solution, you're going to be much better off if you can keep the pH as low as possible, because you're going to get more of it to be able to dissolve. So you're not fighting that common ion effect quite as much. Okay, so today, common ion effect when you're trying to dissolve a hydroxide.